Alright, so today we're going to be doing 5.5, which is trapezoidal rule. So, the idea behind the trapezoidal rule is to approximate the area under the curve using the area of trapezoids. So previously we were only using rectangles, now we're going to be using trapezoids. So this is the formula for area of a trapezoid. You may or may not remember this from geometry. So maybe I'll just tell you quickly about what a trapezoid is in case you forgot. A trapezoid is basically any quadrilateral, four-sided figure that has an opposite pair of parallel sides. That's the only requirement of a trapezoid, okay? And basically the distance between those two parallel sides is what we call the height. Now I know it seems really strange because the height is horizontal in this case, but it's still a trapezoid and that's its height. Its height is always determined between the two parallel sides. That's how you know it's the height versus the other way around. Now the reason we can't determine height this way is because with the trapezoid the height isn't going to be the same at every section, correct? So we want to find height where it's always consistent. So with that, we are going to have the length of our bases. So we have base 1 and we have base 2. So base 1 is this length and base 2 is going to be the other side's height. And we know that we can determine that height by finding the y value at that given point, which we've been practicing doing. And then we would use this formula. Now before we get into that, I want to talk about why this formula works really quick so you get a general idea of what's happening here. So if we look at any of these given trapezoids, you can pick any of them. If I draw in this dashed line intended to be parallel to this line down here, essentially what we've created is a situation where we have a rectangle and a what other shape here? A rectangle plus a triangle. So a trapezoid is essentially either a rectangle plus one triangle or a rectangle plus two triangles. These are always going to be one. So let me show you why that works. So the total area would be equal to, now we've determined right here that this side is base 1, correct? This whole side is base 2. So if this entire side is base 2, what would be this smaller piece of this side here? How could we figure that out? Subtracting. So this little piece right here would be base 2 minus base 1. Do you all see how I was able to figure that out? Okay. So, oh, I'm sorry. Hang on. This piece right here, sorry, I labeled the wrong one, my bad. This right here would be base 2 minus base 1. So everybody understand why that is. Sorry, I labeled the wrong one when I was thinking about it. Okay, so in this case, we would want to figure out what this piece right here would be, okay? So if this whole thing is base 1, we have this side, which of course, this side is of course just equal to base 1 because it's the same thing as across from it if we're just looking at the rectangle. So we know that area of a rectangle, and we've determined this is our quote-unquote height. We know the area of a rectangle is just base times height, correct? Length times width, however you want to put it. So what we just found here is this area. Does everybody see how we were able to determine that? Now we have to find, of course, the other piece, which is going to be area of a triangle. Does anyone remember the formula for area of a triangle? Good, 1/2 base times height. So we have the 1/2, and then we have to determine what those other two things are going to be. So we know that one of the sides, this is a right triangle, so with a right triangle, the two legs are going to be your base and height. So we know that one of the legs is base 2 minus base 1. Everybody understand how I figured that out? And then we know that this other side is basically the same as this, which we would call what? H. So this would give you basically the area of the trapezoid in total. So if we just did a little bit of algebra here, I could rewrite this as base 1 height plus 1/2 height. And then here, we could distribute the 1/2 height out to both of these. So we get B1H plus 1/2 height times base 1 plus 1/2, or I'm sorry, minus 1/2 height times base 2. What you're going to notice now is these two right here are actually like terms, right? They have the same variables. So essentially, it's just 1 minus 1/2. What's 1 minus 1/2? 1/2. So you end up with 1/2 base 1 height plus 1/2 base 2 height. Doesn't matter which order you put B and H in. I just swapped it around. And then if we want to get it back to this formula here, what could we factor out of both of these terms? What do they both have in common? The 1/2 and also the H. So we end up with area equals 1/2 H B1 plus B2. So that's the reason why the formula works the way it does. So if you didn't know, now you know. So any questions about deriving the formula? Okay. So what you're going to notice with this formula is if we're adding the two bases together and dividing by 2, when we add two things together and divide by 2, we're basically finding the what? You add two numbers together, you divide by 2, you're finding the average. So we're finding the average of the two bases times the height. That's how you basically find the area of a trapezoid. So there is a formula here that you can use to make your life easier. You'll see more about why this formula works when we do an example. But essentially this formula works because we have the one endpoint minus the other, so lower minus high, over 2n, where n is the number of subdivisions we have, aka rectangles, times 2, because remember we have to divide by 2 because we're finding the average. And then we have the first y value, the last y value, and the middle two y's. So I'll explain why that's the case. I'll do an example where we don't use the formula, we just use our logic and understanding of what's happening. And then we can group it together and you can see why the formula works. So for this one here, it says use trapezoidal rule with n equals 4 to estimate. And they're giving us what we would call an integral. You guys know of it right now as an antiderivative. And they want us to use n equals 4. That's telling us how many rectangles we need. So if we have 4 rectangles, how many numbers do we need on the interval? 5. So we have 1 in the middle, 1 on the end, we have 2 on the other end. And then we're going to have to split this up a few more times, right? So if I'm splitting it up down the middle, what's going to be the middle number there? Let me make this a little darker. It's kind of hard to see. So what's going to be the middle number here? Yeah, you're right, 1.5. And then what's going to be in between the 1 and the 1.5? 1.25, and then what about right here? 1.75. What is basically the distance between each of these, which of course is all the same, is our quote-unquote height, okay? Our height. So what would be the distance between each of these intervals here? 0.25. So right now all we know is that h, when we do our height of all of our trapezoids, our height is going to be 0.25 because that's the distance between them all, which is the width. Okay, it's confusing because width is height, but same idea. So from here, we are going to have to, just like we always do, we're going to have to find out what each of these heights are because we're going to need to know what they all are to do the math, right? So how could we could look at the graph, of course, here, which would tell us approximately where they're at, but how can I get the exact y value? Plug it in. So I'm going to be plugging into x squared, which is the function. So 1 squared is just 1. So this one has an exact height of 1. 1.25, I'm going to have to do it in the calculator. That's going to be I'm going to round to the nearest hundredths place, 1.56. For the next one, 1.5 squared, that's 2.25. 1.75 squared is 3.06. And then 2 squared is just 4. So everybody understand where I got those numbers from, the heights of each of those vertical. Okay. So remember, our goal is to find the area of each of these trapezoids, and then once we find each of those areas, we are going to essentially add them together to find the total area, correct? So I'm going to do it the long way this time so you can see how it all works. I'm going to find each individual trapezoid's area and add them all up. So for the first trapezoid, we know it's going to be 1/2 times the height, and then it's going to be the product, I'm sorry, not the product, the sum of the two bases. So what is the height of my first base here? 1. What's the height of my second base? 1.56. And you're going to do this process 4 more times, okay? So it's going to be 1/2 times 0.25, and then the next one's going to be 1.56 plus 2.25. And then the next one, same idea, 1/2 times 0.25, and then it's going to be the other two ends here, 2.25 plus 3.06, and then once again, same thing, it's pretty redundant. So what you're going to notice is there is a pattern of some sorts here that you can utilize to help you streamline the actual calculation. So what you're going to notice right off the bat probably is, do you notice that they all start with 1/2 times 0.25? That means we could essentially do what with that value?
Cancel out.
Not cancel it out, but factor it out, right? So I end up factoring that value out. Okay, that's basically the 1/2 times the b minus, that's like where that first part of the formula comes from, okay? That would be 2 minus 1 divided by 4. That's where the 0.25 comes from. Now what you're also going to notice with these, now you could go ahead and do it like this every time, but what you may also notice is, do you see how the number 1.56 comes up twice? And do you see how the number 2.25 comes up twice? And lastly, do you see how the number 3.06 also comes up twice? What do those three numbers have in common in terms of where they are on the graph here? They're in the middle. You see how in the formula it says you can do 2 times the middle y's? That's where that comes from. Instead of doing all of this, you know that the middle ones are going to be used twice, okay? So you have the outer sides plus the middle ones times 2. And then, of course, the end as well. So now do you get a better understanding of why the formula works the way it does? Okay. So then we just basically put all this in the calculator to get a decimal answer. Usually you're going to round to the hundredths place when necessary. So this just takes a second. And you should get about 2.34 when you do the calculation. So does anybody have any questions for me about any of the parts? And do you all see now why the formula works the way it does? So I didn't want to just jump in using the formula because I wanted you to have an understanding of the reasoning behind why the formula works. But now that you've seen it, we can go ahead and use it. Okay. So there's a few things that we want to talk about here. Over approximation and under approximation. We talked a little bit about this with RAM, or rectangular approximation method. We know that when the function's increasing, LRAM is an underestimate. When the function is decreasing, LRAM is an overestimate. And then RRAM is an overestimate when we're increasing. RRAM is an underestimate when we're decreasing. So everybody remember learning about this in the last lesson. So with trapezoidal rule, we evaluate over and underestimation a little bit differently. It's actually based on concavity. Do y'all remember concavity, hopefully? So this one is concave up. Okay, remember concave up is bending upward. So when our graph is concave upward, we know that trapezoidal is going to be an overestimate. This is going to be some vocab that you'll see on the test and quiz as well, just like these. Important stuff. We know that when it's concave downward, where it's bending downward, we know that trapezoidal is going to be an underestimate. Okay, so it's not based on whether the function is necessarily increasing or decreasing, it's based strictly on concavity for this one. Now, why does it not matter? For example, if we have a function that looks like this, would you say this function is increasing or decreasing? Increasing. If we were to use trapezoidal method here, would we have an overestimate, an underestimate, or neither? What do you guys think? Under, over, or neither?
Equal.
It's equal. So that's why concavity matters here versus increase or decrease. Because if your line is a perfect, like a linear function, trapezoidal is actually perfectly equal because we don't have any bends in the function, so it's going to be an exact value for what it is. So just keep that in mind. All right, so let's go ahead and try another one together. I still feel like this pen is a little too dark, too light. So it says use the trapezoidal rule to approximate -1 to 1, the interval from -1 to 1 of sine x squared, using 4 subintervals. So that means that we're going to have 5 values on our number line. So of course the middle of these is going to be 0, and then -0.5, and regular 0.5. So what we're going to do here is we're going to try to use this formula, but in order to use the formula, I need to find all the y values by basically plugging all of these back into the function. Okay? So if I want to find at -1, I'm going to have to do sine of -1 squared to see what that is. Okay? So that's going to be sine of 1, which is some decimal, 0.02. So this yields us the coordinate -1, 0.02. Now we're going to do sine of -0.5 squared. So that's going to be sine of 0.5 squared. And that gives me 0.004. And then I'm going to do sine of 0 squared, which I believe is 0. Yes, it's 0. So that would give me 0, 0. Now, here's the thing on the other side. If I'm squaring -0.5 and -1, what do we know is going to be true when I square these as well? Are they going to be any different? No, so I can just copy down what the other side's going to be, because they're going to be the same. So it just saves you a little bit of calculations that you have to do, because they're all the same. All right. So now that we have all of our y values, we're ready to use the formula. So the formula is going to be t equals b minus a. That's going to be your bigger, like the top, minus the bottom here. So it's going to be 1 minus -1 over 2 times n, which they give us is 4. That's the number of rectangles. And then for the rest of the problem, it's the first y value. So our first y value is this one here. And then the middle y's. So we have to determine what the middle ones are. That would be this one, and this one here. Those are all the ones in the middle. So I don't even have to include the 0 because it's just 0. It's not going to change anything. So it's going to be plus 2 times 0.004 plus 2 times 0.004. You could have also done 4 times it, same thing. And then my last endpoint, I'm running out of room here, hang on, is going to be 0.02. And then we would just put this in the calculator to get our value. So I end up with 0.02 plus 4 times 0.004 plus 0.02. And that's going to be 2, or 1 minus negative 2 is going to be 2. So times 2 divided by 8. And that gives me a really tiny value of this. So any questions about the process? Okay. And then the last one we're going to do, there is a typo on your paper. So you see how it says f of 1 equals 13? That should be f of 8. We have 2 values for f of 1, that's not possible. So you're going to change it to f of 8 instead of f of 1 where it says 13. So go ahead and do that real quick. So it says, if the x values of the interval are not evenly divided, trapezoidal rule does not apply. Use geometry instead to estimate the area under the curve. So what you're going to notice in this picture is, do you see how these trapezoids aren't of equal width or height? They're all different. That is going to change the ability for us to use the formula, of course, so we're not going to be able to use it, so we're going to just have to calculate each one individually and add them all up. So we're going to do a sketch of this one. We have to make sure that our x values go from 1 to 12. So I'm going to go by 2s, just a little easier. This might not be big enough. You can kind of extend it out. And then we know that my y's are going to have to go from 2 to 17. So you can either go by 2s. We can just keep going by 2s. You might just have to add a little extra at the top there. So it goes a little bit high there. So it says approximate, so we're going to do a sketch. So I know that at 1, we're at 2, so we're somewhere about here. I know that at 5, we're at 10. I know that at 8, we're at 13. And at 12, we're at 17, so way up here. So you're going to end up with something like this, and you can connect this curve. And then because we're only doing it on a certain interval, you can actually just create like a box it in if you want. So essentially what we're going to do is each one of these values from 1 to 5, that's going to be the first, represent that first trapezoid. So from 1 to 5, that's trapezoid number 1. Trapezoid number 2 is going to be from 5 to 8. And then trapezoid number 3 is from 8 to 12, which we've already created. So we're going to have to find the area of these 3 trapezoids. So our total trapezoid area is going to be equal to, now, no matter what, notice that it doesn't matter what trapezoid you're finding the area of, it's always going to be multiplied by 1/2, right? So all of these I can multiply the outside by 1/2 because they're all going to be multiplied by 1/2 anyways. So you can put that on the outside, just to start. And then we don't have to worry about it throughout the process. Now I know what I'm going to have to do is, I'm going to have to find the height, aka the width of each of those. So what would be the width from 1 to 5? 4. And then it's the 2 y values, so 2 plus 10. What's the width of this one here? From 5 to 8? 3. And what are my 2 y values? 10 and 13. And then lastly, the last width is going to be pretty big. It's, again, it's 4 actually. So it's going to be 4, and then it's going to be 13 plus 17. And then you would just do the math here. So it's just a lot of plugging in numbers. And you should end up with 118.5. So do we have any questions about any of this process? Okay, I'm going to hand out your homework.